Let's take a look at the commercial advantages of the Level 2 ERTMS application without lateral signaling. In urban hubs and also on the line, one of the most sought-after improvements is increased capacity and timetable flexibility. ERTMS allows for increased capacity and flexibility compared to traditional signaling systems. In addition, compared to traditional systems, up to 60 seconds can be gained for each train that crosses another train in single-track stations or for a diverted entry when we give priority to another train. We can gain up to 30 seconds when we resume running after a signal warns us of an upcoming stop signal that is then cleared. We can gain up to 2 minutes for each train crossing on single-track lines at a station equipped with an underpass, as we do not have to wait for the traditional equipment to clear. We can gain up to a few minutes for more flexible management of the static speed profile of the line. The number of tracks can be increased thanks to an increase in simultaneous movement at the station. The 150 km/a speed limit can be exceeded on lines with train speed protection systems. The time required to manage all slowdowns can be reduced, as can the time required to close level crossings. Information provided to the public will be more accurate and continuously updated on train progress. Let's take a closer look at how this is possible. Increasing capacity and timetable flexibility is possible if the land and trains are equipped with ERTMS infrastructure. In urban hubs where not all train fleets have the special high-density configuration yet, ERTMS allows for denser fleets but also allows trains that are not yet equipped to pass through. Obviously, when all trains are equipped with this crucial system, performance will be even better. Here we see line densification for ERTMS train fleets or mixed fleets. The concept of train integrity is at the heart of densification with ERTMS trains. In this slide, we see train congestion at the station, which can also take advantage of the use of physical track circuits. The concept of train integrity is fundamental for lightening the technological infrastructure of lines or stations while safely bringing more trains closer together. Smaller itineraries will have to be created at stations, making use of existing track circuits. The concept of virtual sections, thanks to train integrity and also the covering of the exit zone of the section, which is also virtual, is fundamental for optimizing train density and maintaining a good cruising speed for the fleet of trains following each other. The use of train integrity and release speed calibration allows, depending on the proximity of the preceding train, optimization of the speed of the following train, safely ensuring that it does not come to a halt. The table shows the average speed of trains following each other depending on how close they are. The closer they are, the slower they go to make sure there's enough space to brake, but the goal is to limit train stops. How can I see where the next train is? I need to know where its rear end is. Traditionally, ground-based devices such as track circuits or contactors are used. In ERTMS, train integrity detected directly from the train and continuously updated via radio to the ground can also be used. It is clear that the advantages are not only in terms of performance but also in terms of maintenance savings for the infrastructure operator. The simplest way is to have the head computer and tail computer communicate with each other, and in the event of any failure in communication, trigger an alarm to be sent via radio to the ground. In addition to densification, there is a need for simultaneity at station entrances and exits. This is regulated by safety constraints in station equipment. Thanks to flexible management of release speeds, ERTMS allows for more simultaneous routes than a traditional system. The first complete ERTMS station without lateral signaling is Bologna, where ERTMS has enabled 6 additional train tracks to be created compared to those allowed by a traditional system. All this has been in operation for 10 years. Imagine the number of extra tickets sold and the commercial advantages, achieved thanks to these 6 additional daily tracks created in a relatively small and simple station. The approach to diversion routes allows ERTMS to manage speed reductions at the point where such a reduction is actually necessary. In traditional systems such as SCMT, speed reductions start from the light signal, so 40 to 60 seconds are lost at each crossing or diversion entrance due to priority being given to another train. The ERTMS system, on the other hand, allows speed reductions to be applied at the point where they are actually necessary, thus avoiding unnecessary delays. The ERTMS system also allows for the implementation of a system of speed restrictions based on the type of train, the type of track, and the type of signal. This can also be seen more extensively if there are multiple consecutive deviations. On a single track line, when there is a crossing with another train, one of the two must wait for the station apparatus to set its route after waiting long enough for the other crossing train to stop. With ERTMS, the ground system and station apparatus know when the train has stopped without having to wait for a set time, which can be as long as 2 minutes. We can therefore save up to 120 seconds per train crossing with ERTMS. Authorization for a train to move in traditional discontinuous systems may not be updated immediately, as is the case with ERTMS, which is constantly connected between ground and board via radio GSMI. Without this system, each failure to update in the event of a new green light causes an average loss of 30 seconds to our journey. Also, the management of slowdowns due to works or particular characteristics of the traction unit of the entire train, such as axle load, is optimized with ERTMS, reducing many time-consuming tasks. With ERTMS, it is possible to impose this restriction only at points where it is actually necessary, for example, at specific engineering structures. Increasing the speed of a railway line without changing the infrastructure is possible with ERTMS because it is a system that continuously updates the information provided to the driver on his interoperable dashboard. Therefore, on lines with traditional discontinuous protection systems, which are in any case limited by regulations to a maximum speed of 150 km per hour, ERTMS can lead to an improvement in line speed, infrastructure, and rolling stock permitting. The constraints of the static speed profile, such as gradient curves, can be optimized through the use of ERTMS, which offers more granular and precise management. The early closure of level crossing barriers can be optimized based on the actual position and braking capacity of the train. This also applies to station PLs, where closure can be optimized. All of this improves waiting times for motorists. Continuous radio updates of the train's position also enable ERTMS to provide the public with more accurate and continuously updated information.